So in this unit, we've talked about the capacitor and the inductor. Both of these devices are storage devices. They store energy in our circuit, okay, which is a little different from what we've seen so far. So our inductor and our capacitor, they both store energy. The capacitor, its job, it wants to keep voltage the same, and our inductor wants to keep current the same. So I'm just going to kind of compare and contrast our two devices here. So let's talk a little bit about the makeup of the capacitor here. So we've got these two plates, and there's some kind of separation between them, and there can be some kind of material through them as well. So we call that the dielectric material. Dielectric material. And depending on what that material is, we can either set up a strong electric field or a very weak electric field. And we call that property the permittivity of that material. And that's given by epsilon, where epsilon 0 is the permittivity of air, and epsilon r is the relative permittivity of whatever this dielectric material is. So if the permittivity, the relative permittivity of the material was 2, then the permittivity of the dielectric in this case would be 2 times the permittivity of air. All right, so another property we look at when it comes to our capacitor is the area of the plates. So whatever the length is times the width of the plate, that's where we get our area from, the length times the width of the plate. And you can store more charge the larger the plate area. Also, we would look at the distance between the plates. We call that d. So that's the distance between the plates. And those are the 3 factors we look at when determining what kind of capacitance we have on that capacitor, or how many electrons we can store per unit of voltage. So that equation looks like this, where we've got the permittivity of air times the relative permittivity of whatever the dielectric material is times the area divided by the diameter. So what this equation tells us is that if we increase the permittivity of the dielectric material, increase the permittivity, then that essentially is going to increase the capacitance of our capacitor. So again, the permittivity tells us how easy it is to set up an electric field in that material. The easier it is to set up that electric field, the greater the capacitance that we can store. Okay, the area, again, think about, a plate that you would use in your home. A larger plate you could put more food on, right? A smaller plate you could put less on, say a dessert plate. Same thing is true for our capacitor. The larger plate will store more electrons, and that also determines that we would have more capacitance. Now the distance between the plates is a little bit different. The distance right here is in the denominator. What that's saying is that as we move these plates farther apart, we actually weaken the electric field. So, and you can kind of think through that yourself when you think about your magnetic field. If you take a magnet and you put it toward your refrigerator, or toward another magnet that is with the opposite pole, you feel that force of attraction the closer you get those two magnets together, or the further you pull them apart, the weaker that force of attraction is. So as we increase the distance between the plates, we actually decrease the capacitance of our capacitor there. All right, so that's the construction of our capacitor. Let's talk about the construction of our inductor. So a few things influence the amount of inductance, and so the point for our inductor is a strong magnetic field. Okay, that leads to a large inductor. Just as for the capacitor, the goal was to set up a strong electric field. Okay, so going back to the inductor, there are 4 different properties that we look at for the inductor. First off, the core material itself, right here. Now, it could be an air core, or it could be, you know, sheet steel or some kind of iron, depending on what we're trying to do. So, the core material, and we talk about how easy it is to set up a magnetic field in that core material. So, we call that the permeability. I'm going to move this down here. The permeability. I'll make that a little neater. So how permeable a material is has to do with how easily magnetized it is. So if it's a material that can be magnetized very easily, that has a high permeability. And we use for that mu 0 times mu r, where mu is the permeability of air, and mu r is the permeability of the core material, the relative permeability of the core material. So it's much easier to set up a magnetic field in some sort of ferromagnetic material, like such as iron, than it is to set up a magnetic field in air. Okay, so let's also look at the cross-sectional area of the core. Okay, so the area would be pi r squared. Many times you're just given the area. And we also have the length of the core material. And then the number of turns, we call them. That's how many coils we have in our wire. We call that the number of turns, or N, in our equation. So the equation for inductance is that permeability of air times the relative permeability of the core material. If you're using air, then that relative permeability is just 1. So you'd multiply the permeability of air times 1. And then we have N squared times A over the length. So the permeability, again, that's talking about how easy is it to set up a magnetic field in that core material. So the higher that permeability, the greater the inductance, because remember, all of these we're trying to set up as strong a magnetic field as we possibly can. And then the area, the wider or thicker that core material is, and that core and that coil around it, the stronger the magnet as well. The number of turns, we actually square that in our equation. So the number of turns is very important, and the more tightly wound that coil is, the more coils that you see, the greater the inductance. And then there's the length. The length is on the bottom in the denominator, which you know, if you remember from your capacitor equation, that means that the greater the length, the lower the inductance. So the longer this coil is, the lower the inductance. Now, what that means is, if you envision this length getting longer, if we extend that coil longer, but we don't increase the number of turns, you're actually spreading out the distance between those coils. They're not as tightly wound, and that's going to weaken the magnet that we're trying to set up. Okay, so that's the basic capacitor and inductor construction, and how the physical properties of each are related to the actual capacitance or the actual inductance of our device.